NFV, Network Function Virtualization. In telecommunications, Network Function Virtualization, NFV, transforms traditional, hardware-based voice services into flexible, software-driven solutions called virtual network functions, VNFs. This allows operators to run core voice network elements on standard, off-the-shelf servers, COTS, instead of proprietary hardware. Primary applications in voice networks: virtualized IP multimedia subsystem, VIMS, the most critical application for modern voice. NFV virtualizes the IMS core, which manages signaling and session control for high-definition voice and video services like VoLTE, 4G, and VoNR, 5G. Virtualized session border controllers, VSBC. These secure and control IP communication sessions at the network border. Virtualizing SBCs allows them to scale dynamically based on real-time call volume, protecting against fraud and malicious attacks while ensuring quality of service. Virtualized media gateways, VMGW. These handle the conversion of media streams between different network types, example between legacy circuit-switched networks and modern IP-based networks. Value-added services, VAS. NFV enables the rapid deployment of services like cloud-based voicemail, interactive voice response, IVR, conferencing, and call recording as software instances on a shared platform. Virtualized Evolved Packet Core, VEPC. In 4G networks, VEPC handles the signaling and data traffic essential for voice calls, using network slicing to prioritize voice traffic over standard data. Key benefits for voice services: elastic scalability. Operators can automatically spin up additional voice instances during peak traffic hours, example holidays, and scale them down during low usage to save energy and costs. Rapid service innovation. New features or codec upgrades, like EVS for clearer voice, can be tested and pushed network-wide via software updates in hours rather than months. Improved reliability. Through automated self-healing, the Mono framework can detect a failing voice component and immediately restart a new instance to prevent call drops. Cost efficiency. By consolidating multiple voice functions onto fewer physical servers, telcos significantly reduce the floor space, power, and cooling required in their data centers. Security challenges in NFV-based environment. Moving voice services to an NFV-based environment shifts the security landscape from protecting black box hardware to securing a complex, layered software stack. Because voice is a real-time service, security measures must not introduce latency that causes jitter or call quality degradation. 1. Multi-tenancy and neighbor attacks. In a virtualized environment, multiple virtual network functions, VNFs, such as a VSBC and a VIMS, often share the same physical hardware. Side-channel attacks. A compromised non-voice application on the same server could potentially exploit CPU vulnerabilities, like Spectre or Meltdown, to leak sensitive encryption keys or call metadata from the voice VNF. Resource exhaustion. If one virtual machine is hit by a DDoS attack, it can starve the voice VNF of CPU or memory, leading to dropped calls across the entire network. 2. Expanded attack surface of the hypervisor/mono. The software layer that manages the virtual machines, the hypervisor, and the orchestration layer, mono, management and orchestration, become high-value targets. Hypervisor escape. If an attacker gains control of the hypervisor, they gain God mode access to every voice call, signaling packet, and user database, HSS/UDM, running on that physical blade. Orchestration poisoning. An attacker compromising the ETSI mono could redirect voice traffic to rogue recording servers or shut down emergency services, E911, across a geographic region. 3. Signaling and media vulnerabilities. Virtualization often uses software-defined networking, SDN, to route voice traffic, which introduces new risks. SIP/H.243 manipulation. Attackers can inject malicious packets into the virtual switch, vSwitch, to perform call hijacking or toll fraud, where calls are rerouted to premium rate international numbers. Unencrypted internal traffic. While external traffic is encrypted, operators sometimes leave internal east-west traffic, between VNFs on the same host, unencrypted to save performance. This allows for internal packet sniffing. 4. Dynamic compliance and auditing. In a legacy network, security was verified by physical access to a rack. In NFV, episodic life cycles, a voice instance might only exist for 30 minutes to handle a traffic spike. Capturing forensic data for law enforcement, legal intercept, or security audits becomes extremely difficult when the crime scene disappears instantly. Configuration drift. As the Linux Foundation's ONAP automatically scales and updates VNFs, ensuring every single instance maintains a consistent security posture is a major operational challenge. 5. Latency versus encryption trade-offs. Voice is highly sensitive to delay. Implementing robust, deep packet inspection, DPI, and multi-layered encryption in a virtualized environment can add milliseconds of latency. If not optimized using technologies like SRIOV, single root I/O virtualization, these security checks can ruin the user experience. ZTA, Zero Trust Architecture, and NFV in a virtualized voice environment. Zero Trust Architecture, ZTA, moves away from perimeter defense, firewalls, to a model where no VNF, user, or packet is trusted by default, regardless of its location in the network. Here is how ZTA principles are applied to solve the security challenges of NFV-based voice. 1. Identity-based microsegmentation. Traditional networks use IP addresses for security. ZTA uses workload identity. The application, even if a VSBC and a VIMS are on the same physical server, ZTA creates microperimeters around each. They can only communicate if they present valid, short-lived cryptographic identities, example via SPIF/Spire. The benefit: this prevents lateral movement. If an attacker compromises a non-critical VNF, they cannot jump to the voice core because they lack the specific identity token required to talk to the VIMS. 2. Mutual TLS, MTLS. For east-west traffic, ZTA mandates that all traffic, even traffic moving internally between virtual machines on the same host, must be encrypted and authenticated. The application: every internal signaling exchange, SIP/diameter, and media stream, RTP, is wrapped in MTLS. The benefit: this eliminates the risk of internal packet sniffing. Even if an attacker gains access to the virtual switch, vSwitch, the voice data remains encrypted and unreadable. 3. Continuous verification of the mono and hypervisor. ZTA treats the management layer as a potential threat vector. The application, the ETSI mono, must undergo continuous authentication. Every command to spin up or scale a voice VNF is verified against strict policy engines, like Open Policy Agent, OPA. The benefit: this protects against orchestration poisoning. An unauthorized or drifted configuration change is automatically blocked if it doesn't match the pre-approved security manifest. 4. Hardware-based root of trust. To prevent hypervisor escape or side-channel attacks, ZTA links software security to physical hardware. The application, utilizing trusted platform modules, TPM, and trusted execution environments, T, like Intel SGX or AMD SEB. The benefit: it ensures the voice VNF is running on known good hardware and that the memory space used for voice encryption keys is physically isolated and encrypted at the silicon level, shielded from other noisy neighbors. 5. Least privilege access. For automated scaling. The application, when the network automatically scales a voice VNF, that new instance is granted only the minimum necessary permissions, ports, protocols, and database access, required for its specific role. The benefit: this limits the blast radius. If a temporary voice instance is compromised, its restricted permissions prevent it from being used to reconfigure the wider network core. LLM, large language model, and facility and network management. In the context of the highly complex 800 VDC AI factories and NFC we've discussed, large language models, LLMs, are shifting facility management from reactive to intent-based operations. 1. Intent-based networking, IBN. LLMs act as a translation layer between human engineers and complex machine configurations. Application: an engineer can type, provision a new VIMS instance with gold tier redundancy, and the LLM generates the specific YAML or JSON manifests for the ONAP orchestrator. Benefit: reduces manual configuration errors, which are the leading cause of downtime in virtualized environments. 2. AIOps and predictive maintenance. LLMs excel at log summarization and pattern recognition across massive data sets. Anomaly detection. In an 800 VDC environment, an LLM can analyze telemetry from thousands of digital power controllers to identify subtle thermal fluctuations that precede a component failure. Root cause analysis, RCA. When a voice call drops in an NFV network, the LLM can ingest logs from the hypervisor, the VSBC, and the physical switch simultaneously to provide a natural language summary of the failure. The failure was caused by a memory leak in the vSwitch following the 2AM security patch. 3. Automated security and compliance. LLMs are being integrated into zero-trust architectures to manage policy. Policy generation. LLMs can draft Open Policy Agent, OPA, scripts to enforce least privilege access across new VNFs. Vulnerability mapping. Tools like Microsoft Security Copilot use LLMs to map real-time network traffic against the MITRE ATT and CK framework, identifying if a neighbor VNF is attempting a side-channel attack. 4. Interactive knowledge management. Modern network documentation for technologies like GAN/SIC or 800V safety protocols is dense and rapidly evolving. Application: technicians can use RAG-based, retrieval augmented generation, LLMs to query internal datasheets. For example, what is the specific creepage distance required for an 800V busbar in a 90% humidity environment? Value: instant access to ETSI NFV standards or specific hardware manuals during critical repairs. 5. Code and script generation. For net DevOps, LLMs assist in writing the glue code for automation. Application: generating Python scripts for PM bus data collection or creating Ansible playbooks for mass firmware updates across a data center's power modules.